5.4. A little more. We're going to look at sampling distributions, and we'll look at them. We'll look at when a sampling distribution is approximately normal. It's going to be great. So we're going to learn what a sampling distribution is. We're going to interpret the sampling experiment, and then we're going to apply it to find the probability of a sample mean. All right, so here's what a sampling distribution is. It's the probability distribution of a sample statistic. So when we take samples of size n repeatedly from a population, if I took, from us, right? If I took samples of size 4, right, from you guys and recorded your heights, and then I would look at the mean of those. If I had a bunch of means, then I would have the sampling distribution of the sample mean. All right, so when it says we have a population with this, where it says mu and sigma here, this, right? What that means is that the population is assumed to be approximately normal. And the distribution is approximately normal, right? So, say I was interested in the amount of time that students at Cleveland High School spend studying every night, right? I could do repeated sample. So I could take maybe 10 kids from every class, right? Find their mean, the mean number. So I took 10 kids out of one class, said, hey, how many times or how often, or sorry, how many hours you spend studying a night, right? And then I calculate the mean of those 10. There's sample mean number 1, right? I go to another class, and I randomly select 10 students, and I say, hey, how many hours do you study a night? I find the mean number of hours. There is sample mean number 2. And when I do that, repeat it. Once I get that, I get a sampling distribution of the sample means, right? So I'll have a distribution of means there. And I could make a histogram of it. We do a bunch of stuff with that data. Okay, so the mean of sample means, we call that mu sub x bar. Okay, mu sub x bar. It's the same as the population means, right? So it turns out that with that whole how many hours do you study question, right? If I was able to get data from every single student at Cleveland High School, right, and I asked them all, how many hours do you spend studying? I got data from all of them, and I got the mean of all of that, right? It turns out that that's actually going to be the same as the mean of my sampling distribution, right? The mean of all of the means that I got. You know what I mean? I got means from all these samples of size 10, right? It turns out that the mean of those means is actually the same as the mean of everybody's calculation. It's very helpful because then you can assume that you don't have to actually get data from everyone in the population. You can assume that the mean of your means is the same as the mean of the population. It's pretty nice. The standard deviation of the sample means is also equal to the population standard deviation, divided by the square of the sample size. And so that formula that you have down there, sigma sub x bar equals sigma divided by the square root of n, there on the bottom, is very, very important. All right, here we go. Let's look at this. Okay. Mean, variance, and standard deviation. Population. Huh? Interesting. All right, so we're going to skip that question because it doesn't actually really fit in. So, sorry. This is more fitting. And it's also, it's a really weird question when you look at it. In order to find all of those things are meanings for, you have to create probability distribution. Is really actually quite complicated. Actually, it's actually like I wouldn't even give a problem like that. No. All right. So, but if you were to graph that probability distribution, it will look approximately normal. If we see a graph that looks like I could nicely fit in a bell-shaped curve, we're going to say that if it's looking approximately symmetric, we can usually say that the distribution appears to be approximately. All right, so the central limit theorem tells us that if we get samples that are greater than or equal to 30 from a population that is normal, then the sample means approximates a normal distribution. And in fact, it works for a population that's not normal as well, so for any population. So this population here, right, if I had a graph of it, it does not look like a normal distribution, right? But if from this nasty looking population, I take repeated samples that have a sample size greater than or equal to 30, and I look at the distribution of those sample means, it turns out that that distribution is going to be normal. So it's going to take a distribution that looks all yucky like that and turns it into something that looks very nice. Something that we can use, that we can calculate probabilities using normal distribution. That's the whole point. It makes it so much nicer when we can do that. You know what I'm saying? We can get out our z-table, we can get a z-score, and then we can calculate a probability based on a z-score and a z-table. This pretty much says the same thing, except for if you're sampling from a population that's normally distributed, it doesn't matter what your sample size is. You can assume that the sampling distribution of your sample means is also normally distributed. This right here is not crucial. Pretty much just reiterating the same thing that we said before when we were talking about means of, sorry, uh, the distribution of sample means, right? Same stuff. So these are the same formulas. All you need is, if you've already written these formulas down, then we're good. Okay? You just need to know that the mean of the sampling distribution of sample means is equal to the mean of the population, and that the standard deviation of the sampling distribution of sample means is equal to the standard deviation of the population divided by the square root of your sample size. You've already got that written down. And you've got it. So just some interesting pictures. I'm just comparing some distribution that's nasty and showing. So we got a nasty one. We've got a normal population distribution. We got a distribution of sample means. Just comparing them. Really not. Just kind of to get it here. It's not something you'll refer to in the future. All right, so let's look at this. Cellular phone bills for residents of the city have a mean of 63. And a standard deviation of 11. Random samples of 64 cellular phone bills, so the sample size, what that means is my sample size N is 64, are drawn from this population with the mean, we get the same mean, just what it says. So we're going to find the mean and standard error, or standard deviation, of the mean of the sampling distribution. Then we're going to sketch a graph of the sampling distribution of sampling means. So, we got a formula that tells us that the mean of the sampling distribution is the same as the mean of the population, which means that it's just 63. We also know, I'm going to have to write this somewhere else, right? That if our sample size is greater than or equal to 30, then the sampling distribution of the sample means, so I'm just going to write sampling distribution. Sampling distribution is approximately normal. So that means I have all the information that I need, so I'm going to bring this up to fill in space. That means that I'm allowed to represent this as a normal curve, where my mean is 63. Now, in order to complete this picture, I would like to know what the standard deviation is. We have our formula that tells us that the standard deviation of the sampling distribution of sample means is equal to standard deviation of the population divided by the square root of the sample size, which in this case is going to be 11 divided by the square root of 64, which turns out to be 11 divided by square root of 64 is 8, right? I'm going to go ahead and get a decimal value for that. Approximate value, probably. Actually, it's equal to 1.37. So now if I was going to complete the picture of this, I'll also put in the standard deviation, right? So in this case, one standard deviation away from the mean is going to be at 64.375. One standard deviation below the mean is going to be 63 minus 1.375. 61.625. We've got two standard deviations below and above, and three standard deviations below. But this gives us a nice picture of the sampling distribution for this year. Also, just want to point out that when I'm describing a distribution, I'm going to describe three elements, okay? I'm going to describe shape, which is that. I'm going to describe a measure of center, which is my mean. And I'm going to describe a measure of spread, how spread out the data is, or how much variation there is in the data. And that is what our standard deviation is. Standard deviation is a measure of spread, mean is a measure of center, and shape, you said that it's approximately normally distributed, so the shape is normal. In fact, we've not really described a distribution fully. Right? So, the diameters of fully grown white oak trees are normally distributed with a mean of 3.5. Always going to write that stuff down when I see it. Standard deviation of 0.2 feet. Random samples of size 16, which means that n and 16 are drawn from this population. The mean of each sample is determined. We're going to find the mean and standard error of the mean of the sample distribution. Now we're going to sketch a graph of the sample. Okay, so the mean then of the sampling distribution, or the sample means, distribution of sample means, is going to be 3.5. It's going to be exactly the same as the mean of the population. The standard deviation is now going to be 0.2 divided by the square root of 16, which turns out to be 0.2 divided by 4, or 0.05. I'm not going to draw the sampling distribution yet. I think we're good with where we're headed. We're headed at actually calculating probabilities. That's the direction. Alright, so we're going to get a z-score using the distribution of sampling distribution of sample means. Only change that we're going to do is, instead of using the standard deviation of the population, we use the standard deviation of the sample means. No problem. So now we're ready to actually do some problems. These problems are a lot like the problems we were doing in 5.3, and one of them is even exactly the same type of problem, right? Where we have a normal distribution, we're given the mean, standard deviation, and some value, and we need to figure out what the probability of that value occurring is, right? And so that's what we're going to do here, except for now, we're going to have a sample, and we're going to find out the probability of that value occurring for many samples. So here we go. In this case, we got lengths of time people spend driving each day. If we randomly select 100 drivers, so if it says we randomly select, or it says, hey, you sample it right away, I'm going to say that's what n is, okay? N is always my sample size. And in that case, what it's telling me is that my sample size is 100. We want to know the probability that the mean time they spend driving each day is between 24.7 and 25.5 minutes. They want us to use a mean of 25 and a standard deviation of 1.5. Alright. So, what we're being asked, and we're going to assume, because of this graph here, we're going to assume, right, that this, when it looks fairly symmetric, right, we're going to assume that it's approximately normal, so that we can go ahead and use a normal calculation. So with that in mind, then, it looks like what we're going to be looking for is this is 25. What we're looking for is 25.5 and 24.7, something. I'm not sure if that's exactly what it's going to be. But what I really want is a characterization of what I'm trying to find. I'm trying to find this shaded area. All right. But now we have a sample. So what we're not really actually using this mu and this sigma. We're actually going to be using the mean of the sampling distribution of sample means, which turns out to be the same thing as the mean of the population. But what's going to change here is we're not going to use this this standard deviation. We're going to use the standard deviation of the sampling distribution of sample means. Which, remember, uses the formula that we have the standard deviation of the population divided by the square root of the sample size. So in this case, that is going to be 1.5 divided by, sample size was 100. So we're looking at 1.5 divided by 10, which is all right. So at this point in time, I'm just going to write this down here so I know what this is. I have two options. I can go straight to my calculator, which is quite frankly the easiest way to do this. Or I can use a z-table, right? What I'm looking for, really, so I'm going to write this out longhand, and then I'm going to just do it on the calculator. But what I'm looking for is the probability that z is between, remember I'm going to use the x minus mean divided by standard deviation, but in this case, it's the mu sub x bar, and my standard deviation is actually we've already calculated this thing. So what we're looking for is the probability that z is between 24.7 minus 25 over 0.15 and 25.5 minus 25 over. Sorry, those things are running into each other there. I'm going to move this over so it's don't worry, nothing has changed in your notes. So I mean, before what you do, right, is you would find this z-score, right? And then you would find, sorry, you would go to your table, right? You get the z-score. And then go to your table and find an area. And then you would find this z-score, go to a table and find an area. And you would subtract this one, right? You would go subtract from this one. So you would go this minus this, and you would get your area, right? So that's the way to do it with the z-table. Yeah? And I think that we'll go ahead and just do it, and then I'll do it with the calculator too. And then from that point on, I'll just do it with the calculator. So let's go ahead and calculate that. We're looking at the probability that let's go 24.7 minus 25 divided by 0.15 is negative 2. 25.5 minus 25 3.33 approximately. Okay, it's probably going to be a fairly huge number, actually. Okay, so what does that equal to? Well, we can go to our z table, and we will find an area, first of all, for 3.33. It's probably going to be very large. Oops, wrong one. 3.33 positive, right? 3.3 positive. I don't know what I just hit over there, so that's messy. Alright. So that is 0, 1, 2, 3. 0.9996. So 0.9996 minus, and now we'll find an area for negative 2. Negative 2 is all the way up here somewhere. And it's just straight up negative 2. So we got 0.0228. .9996 minus 0.0228 is 0.9768. So that's what the probability is. So we did that just using a z-table first. If we weren't going to use a z-table, what we're going to do is go normal, CDF in the calculator. Remember, our lower bound is going to be 24.7. I'm going to run out of room to write that, so I'm going to put it below. So if we use the calculator, so alternatively, use the calculator. In which case, I would just put normal CDF 24.7, 25.5, comma 25.5, comma mean, comma standard deviation. We'll put that in and we'll get something. When would I do that instead of doing the z-score? I would do it immediately, so I could do it right after this, or I could do it before. If I wanted to be super thorough, I could put it right there. But at this point, I mean, as soon as I've got all my calculations done, I can just go to the calculator. It's okay. So let's go ahead and get this using our calculator. Get out the handy-dandy calculator. I can do this from my scratch pad, so I can hit the calculator button over there. Okay, menu, same thing we've been doing the whole time. Probability, distributions, normal CDF. Our lower bound we said was 24.7. Upper bound is 25.5, right? Yes. Our mean is 25. Standard deviation, 0.15. Better get the same answer. Surely. Got the same answer. So, there is a long way to do it. If you like it that way, if you like to use the table, knock yourself out. I know people that like it, like to do it like that. And it's okay. It is acceptable to just do this, right? And so, you could go straight from this point, straight from the drawing, all the way to that. Though, if you are going to do that, you need to answer this is your complete answer, okay? I'm going to use the calculator. That is your complete answer. And you got to include the drawing. All right, got it? So you could just skip all that, and the circled things would be pretty much your answer. Okay? So let's go ahead and do it that way for the next one. Just wanted to show you every single way of doing this thing. Okay? Just wanted to show you all angles, all approaches. All right, let's do another one. Okay. The average price of a single-family home in the United States is, wow, that's expensive. Homes are fairly inexpensive here in New Mexico. So. Yeah, I mean, for that price here in New Mexico, you could own a house on the river in River's Edge. I've seen. And it's not a big house, but a very small house with a beautiful beach. A view of the Rio Grande? A beach? No, a beach if you want to call it that. Yeah, it's not a beach. It's dirt. It's not sand. It's dirt. If you can make clay out of it, it's dirt. All right. So we're going to randomly select 12 single-family houses. And by the way, the average price is that, so I'm going to assume that my mean of my population is 290,600. And it tells me that I randomly select 12. So randomly select 12 tells me that n is 12, that my sample size is 12. What is the probability that the mean sales price is more than 265,600? We're going to assume that it's normally distributed, and ooh, there's my last bit of information I need. I need a standard deviation of 36,000. So what am I looking for? Let's draw a picture of the area. We got our mean here. We're looking for more than 265,000. So if our mean is over here at 290,600, then 265,000 is somewhere below, somewhere about there, right? So we're looking at finding the area of this shaded region, right? Stuff that's more, bigger, greater, above. So in order to do this, we need to calculate the standard deviation, our sample standard deviation of the sampling distribution of the sample mean, which turns out to be, right, the standard deviation of the population divided by the square root of the sample size. Whoa, 36,000 divided by root 12, around 10,392. I'm going to go ahead and just leave it. There's some decimals. We're talking about the tens of thousands and hundreds of thousands. I think that's sufficient. All right, cool. Now that we have that information, we can go ahead and just go normal CDF. Our lower bound is 265,000. Our upper bound is as close to infinity as we can make our calculator say. And then our mean is 290,000. Standard deviation 10,392. We'll put that in our calculator, and we will get an answer. Menu, probability, distributions, normal CDF. Lower bound was 265,000. Upper bound, something like infinity. 290,600. Oops, I put a decimal. Wow. 10,000. Oh, nice. Thank you. And pretty high chance. All right, so our probability is around 0.9931. And done. Yeah. So I did just change that right there, made it a 6. The answer's right. So that's the mean, yes. Oh, I put the 6 in the wrong place. Thanks. Good grief. Up, 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 and now big eraser. Well, I was on such a I'm going to just have to write it big. 290,600. Alright. A lot of commas in there. Looks weird. That's okay. Ready to do another one? Alright, let's do another one. So, LCD computer monitors are normally distributed with a mean of $190 and a standard deviation of $40. Hey, anybody pick out what's different about this from what we did last time? That's true. They're smaller numbers, but something is going to change the way we do this problem. It's tricky because it looks almost the same. That is different about it, but I mean it's like different from all the problems that we've done for kind of a glaring reason. That's alright, I had to learn the line dumb, so it wasn't that good. So there's no sample. We're not sampling. It's actually talking about the population already, right? So we don't have to do that calculation where we do the standard deviation divided by the square root of the sample size, because there's no sample size. So this is just straightforward what we're doing at 5.3. So let's go for it. What are they asking for? They're asking for the area of the shaded region, if this is normally distributed, with a mean of 190, and we want to know the probability that it costs less than 200. So we want the area of this shaded region. We'll just go ahead and go normal CDF. Our lower bound is going to be negative 10 to the 99th power. Upper bound will be 200. Our mean is 190. Standard deviation 48. Plug that bad boy in the calculator, and we will get an answer. Boom. I'm even going to skip the middleman and just go in there. And lower bound was negative 10 to the 99th power. Upper bound was 200. Mean was 190, I believe. Standard deviation 48. Yes. Enter. Approximately 0.5825. Done. Boom. No problem. All right. Well, that was just what we did in 5.3. So why are we doing this? We're going to compare it to the same probability if we look at, or I don't know, it's the same, but the same situation using a sample. Yeah, it's exactly the same. So what if we randomly selected 10, right? What's the probability that the mean of these 10 is less than 200, right? So in this case, my mean is going to be the same as the population, 190. But now my standard deviation is going to be different. It's going to be the standard deviation of the population divided by the square root of the sample size. too fantastic to take notes. No? I mean, if you are, I get it. It's happened before. So that is approximately 15.18. All right. So now, what are we looking for? The situation has changed slightly. Not the picture, though. The picture is the same. $190, $200, less than everything below. But now we're going to calculate normal CDF, lower bound negative 10 to the 99, upper bound 200, mean 190. Standard deviation is different though. It's 15.18. The standard deviation for our sample looks like that. Let's go ahead and see how that's different. Check it out. Standard deviation got much smaller. It's now 15.18. Thank you. So we come up with a much higher probability. The probability that the mean of that sample is less than 200 turns out to be extremely high. Or much higher, I would say. I mean, that's considerably higher. 0.745. So we would say that the probability that the sample mean is lower than 200. Is much greater than the probability that one randomly selected monitor cool. And there we go, there's a 5.4 summary. That's what we did. And that is the assignment for 5.4.